Okay, I think we can start, right? Yeah. First, let me do the introduction. My name is Alexey. As I said before, I work for FP Complete. The project I'm going to be talking about is my personal hobby project, just because I needed it. An array library, there was not a good one. Well, there are not as good one. Anyways, I rarely do public speaking talks of this kind, and especially I've never done a workshop like that, so it's going to be a new experience for both of us, I mean for all of us. And hopefully I'll learn how to do these kind of talks, and you learn something about arrays, so it's going to be a win-win. Most of the time, I'm not going to be standing here. I don't have any slides, so I'm not going to bore you with a chicken hypnotizer. Just in case you don't know, that's how you can, there is a way to hypnotize a chicken, and that's how you can do people with slides. Look it up, Google it, it's a real thing. Sorry, sidetracked. Let me go ahead and turn on the light so it's going to be more visible for you, and we'll start. Also, here's the repository. If you want to go along, you don't need to clone it or anything. You don't need to really build it. But if you want to, feel free. All of the examples are there. And okay. First of all, I want to start with what an array. An array you can think of normally it's a mapping between an index and an element, and it can have multiple dimensions. Usually we deal with vectors, but sometimes we need more than that. Haskell is a pure language, so we tend to use abstractions like map or fold or zip with and such. For that reason, but we also live in a pure world. So as a pure array, you can't do mutation on it. It's an immutable thing, which has a lot of advantages. But sometimes we also need to do mutation and all the nasty stuff that comes in imperative languages. Okay, so let's go ahead and start with something simple. Every function, almost every function, deals with this type family. If you don't know what type families are, you don't need to sweat it. Don't worry about it. Sorry guys, I started early without you. Let's look at how we can construct an array. This is a type signature for one of the most useful functions in the library. I will go one by one at all of the arguments, and throughout these talks we'll learn more about all of them. First argument we got to give to this function is computation strategy, which is this thing. For now it's just seq, which means sequentially, compute sequentially. We'll talk more about the other ones. Then we give an array a size. In this case, we're going to give it a size of half of the argument that we got here. And we give it a function that's supposed to map from an index to an element. And we get back an array. And here's the function, which does just multiplies an index by 2. So this will give us an array of even numbers. So let's try it out. Okay, it sure does. It gives us five element array with all of the even numbers. Now there is a P, a weird thin letter here, which is a representation of an array. As in other languages, you can represent array in memory in different ways. It's always going to be, we're going to be talking about rectangular arrays. There is implementations of jagged array, which is not rectangular, oddly shaped. But they all represent either by a contiguous chunk of memory. Let's say if it's int 32. Right? It's a 32-bit integer array holds this. Then an efficient way to represent it is just contiguously keep it in memory. If you have something, some data type that is extremely weird, like I don't know, a sum type, then you can only have boxed arrays, which is an array of pointers to elements. And I will talk a little bit more about this. But the basic one, the most efficient one, I would say, is a primitive array. And it can store any element that is an instance of a type class prim. Let me do this. Okay. And there is a whole lot of instances for this class. Let me see. You can always look it up on Hackage or in documentation. It comes from a package called Primitive, which is one of the base libraries that is being used by Massiv. But for some strange reasons, bool is not considered a primitive in Haskell. There is no primitive type bool. Actually, its memory representation, it's implemented as sum type true or false, which makes it not a primitive value. So there is an array type called storable that can keep these kind of elements, just as well as in integers, doubles, and the rest alike. So this will give us something weird happen. Okay. And as we expect, it gives us an array with trues and false for evens and odds. There is a big difference between this primitive and storable. Primitive arrays, they are managed by GHC. So at any time, it can, in order to improve memory fragmentation, it can go ahead and move this array into a different location in memory. As such, it is impossible or it's dangerous to pass it to foreign libraries, to a C world, because it can disappear and you point at this address. For this, what you want to do, you want to use storable. And then you can just get a pointer. There is a function that allows you to do it in Massiv. It's a very low level, so I don't suggest you using it. But if you do need it, you can. And then you can pass it to a function in C that you found online on some Stack Overflow question that does extremely fast algorithm to something. So it's possible. The next interesting representation is U, which stands for unboxed. It's sort of like a primitive, but it's a bit trickier. It comes from a vector package. Anything that is an instance of unbox class can be stored in this type of array. Oh, and by the way, for storable, for S, there is also a class for elements which is storable. As you can see, in order to make an instance of this class, you have to implement a bunch of weird, dangerous stuff, deals with pointers, and so you don't normally want to touch those classes, but you can look at the instances, the data types that have instances of this class, and you can safely store them in the arrays of this representation. And for example, neither storable or primitive can keep tuples, can work on tuples, which is kind of unfortunate. But unboxed can. Oh, can you see? Should I make it bigger? Is it better? Maybe like that? Oh, you were okay before. Huh?
This is good.
This is good? Okay. Okay, so what it does underneath, it will take an array of tuples and convert it into a tuple of two arrays that are primitive arrays. And it does in a very tricky way. This implementation is very interesting. If you ever want to learn this kind of stuff, just look through the vector package source code, and you'll have fun. Now we get to the data type that is a maybe int. Maybe it cannot be unboxed. So you cannot have an efficient representation for it. For this reason, we have to use the box data type. And if we look how to construct it, it's same thing. Go create an array, sequential, we give it a size. So this one will, oh, I totally forgot about this second type argument. It's all of these functions were creating just a vector, so it's not a multidimensional. It's just a flat array of dimension 1. We give it a size, and we give it a function that will return just and nothing on evens. We run it, and we get a boxed array of size 6, and as we expected, just 0, nothing, just 2, and so on. Those arrays that I just showed the representation, they're your classic arrays that are backed by real memory. We'll talk about more functional arrays in the next session or a little bit later. But for now, I want to talk about the boxed representation because it's the most common thing to do in Haskell. For example, when you have a list, list will be a list of pointers to things. It doesn't matter if it's an int or it's just or what have you. It's always going to be a pointer. So this is an example. I want to ask all of you, what do you think the answer will be? This is a list with 3 elements. One is undefined, and the last element is also an error, and the middle one is C. And we want to get index this element C. What do you think this the answer for this will be? Anybody? That's correct. Despite that we have 2 dangerous things in both positions, it happily pulls out a C for us. This is because this element, as far as list is concerned, is a thunk. This is also a thunk. And this is a thunk. But when we pull it out, it will, and print it, it will evaluate it to a normal form and print it happily for us. So let's go ahead and see how it works in arrays. We create an array. This is an unboxed representation. And we create an array with 10 elements. And for any even one, we'll basically put some, it's called bottom. We'll put a bottom an error there. And we evaluate it. And it will give us an undefined error. This is because unboxed, primitive, and storable arrays, they are always evaluated to a normal form. It's a contiguous chunk of memory. There is no thunks, there is no pointers, there is nothing that allows us to run into a situation like that, because it will always evaluate all the elements and actually and efficiently store them in memory. So if you're looking for performance, use one of those 3. What about boxed? This is similar to an example before. It's an array of pointers. What do you think this answer will be? We just converted the same list. We're using the function from list, and we create an array, which looks exactly like that. The answer is it will be an error. The reason why, because boxed arrays, they keep all the elements to weak head normal form, which means, if you're not familiar with that, it will, if we'll take a maybe example, and we evaluate an element of that is a maybe, and it will know that it's either it's just or nothing, but it will not know what type of element it just holds, because it is evaluated to weak-head normal form. A normal form, on the other hand, will evaluate the whole structure fully. That's the difference. And this is applicable everywhere, not only in arrays. This is very important to know. This is how we introduce memory leaks. Let's say if you use fold L, for instance, without a tick on it, and the accumulator is not strict, then you watch your memory blow up and your computer die. And yeah. For that reason, I made sure that array elements in Massiv are always strict. This prevents a lot of problems from happening. Same thing in this example, despite that if you think this is index 0, this is index 1, we don't go any farther. We don't need to get to that element. Arrays are not sequential. We evaluate the whole thing as a data structure, so this will also give us an error, despite that we're not getting the last element. I want to sidetrack a little bit from this, and I want to ask you guys, if you at any point you have a question, please interrupt me. Don't hesitate. I would like that to be a discussion. This will make it easier for me, because I'm not even sure, if I'm making sense, if it's too important for you, if it's or if you're learning something new, which is great, then feel free. Okay. Now let's look at this example. As I was telling you, if it's an array of maybe characters, what do you think the answer here will be, considering what I've told you? Perfect. It will happily keep those just undefined because it's just a pointer to something that doesn't exist. And same thing happens here. It works just fine because it's a string, and a string is a list of characters. So this works just fine. There is also an extra representation, and stands for N. It stands for normal form. It's a boxed array that all elements are kept at normal form at all times. This is a crucial for especially parallelization. If you're trying to evaluate all of your chunks of array, and you're trying to get the performance out of each worker thread that does computations and such. I'll talk, by the way, about that more later. You want those workers to evaluate the elements all the way down. Make sure they split the work, not just evaluate some things and be done with it. In this case, this will be an error because it will evaluate each element, including this full string, and gives you an error. And as I said, it has some performance consideration. All the representations perform slightly differently. Storable and boxed and primitive will always, not always, most of the time they will have very similar performance, where normal form and the boxed arrays, they will be always slower. And so let's take a look at it. We'll just use a function, parabola. Everybody familiar with it? It's mapping from next to a square. And we create a big array. We'll create a very big vector and see how long it takes for it to be created. Have you seen before criterion output? Nope. We'll look at it. Let me go ahead and make this a little bigger as well. This is your friend in a performance world in Haskell. Whatever you write, try to benchmark it, because it's very hard to get the performance right in Haskell. GHC is a very smart compiler. It will do a lot of optimizations for you, and it will be very fast until it can't. And when you forgot a bank pattern, or you forgot to do something, an inline pragma, some sort of optimization, and the performance can be an order of magnitude of 100 slower. So benchmark is always a good friend for it. As I was saying, creating a large parabola sort of data for storable and primitive will give you the same very similar performance. This how long it takes, and for the most part, you don't need to pay attention to these numbers too much. If you want to learn more about them, just read up criterion documentation. But the performance for unboxed, same as for storable, but now we get to boxed arrays, and they are 40 times slower. So the moral of the story is whenever you can, keep your elements either unboxed, primitive, storable, and you will get much faster code. But if you can't, it's okay. You will take a hit, but you can still work with those data types. You don't need to worry about what this function does. It's just for a little expensive function from chaos theory. And we will try to create an array, large array that takes a long time to create. And we're going to do it as a weak head normal form, as a normal form, and also parallel normal form. As you see, we changed the computation strategy from seek to par, and it will automatically parallelize the computation for us. And how it's going to do it, we'll talk about it later. Let's go ahead and do maybe. Now let's look at weak head normal first. Oh, look at it. It's so fast. It's much faster than previous. But normal form is so much more expensive. What's going on? Oh, well, yes, that's right. It just evaluates the thunks, but the data is never really evaluated. Watch out for these kind of benchmarks, because it doesn't give you full truth. It never did any work. It just created an array of pointers, and that's why it was really, really fast. When evaluated to normal form, or you see here, let me actually show you how those benchmarks implemented, so it doesn't look like a. Even in criterion, there is. In criterion, there is a special operator that will force the array to a normal form, or any element to normal form, and a weak head normal form for this particular purpose. So even in benchmarks, you will get the real performance, not speculative. Now let's look at this too. It did exactly the same operation, but this was done sequentially, and this was automatically parallelized for you. So all you had to do was to change one argument, and you got the full benefit of all of your processors on the computer, which is great. That's exactly what we want. Okay. Any questions so far? On the representations, does it make sense, the boxed primitive stuff? Okay, great. Now let's move to something that is we don't have in an easy way to do in other libraries in Haskell world, in arrays. It's namely the multi-dimensions. But before we do this, we need to talk about how indices work. First, I thought creating tuples, using tuples as indices would be a good idea, until I realized it's not. There's multiple problems with tuples. First of all, they're too lazy. Same thing, every element is going to be a thunk. Then they're too polymorphic, so they can keep any sort of elements. And in order for you to know what's in there, you need to explicitly give it a type signature. And they don't scale very well to arbitrary dimensions. I mean, there's very, very big tuples. I don't even remember, like 64 or something. I don't remember what's the biggest tuple in Haskell is, but they're limited. And that's not the real problem. The real problem is creating instances for classes of those tuples. It's way too much boilerplate, and I wanted to avoid that. For that reason, I created. By the way, there is also more seats in the back if anybody needs it. And there is a whole couch. And extra chairs will help. But nevertheless, there are instances for up to 5 tuples in arrays, so you can use them if you really want to create arrays and index with tuples. Here we have a little operator. It's kind of like dot in lists, enumeration. And this will give us a 3-dimensional array indexed by tuples. And there it is, with nice, pretty printing. But you see, we had to give it a signature that it is int, and the same for the element. There is type synonyms that you can use to make it easier. Less typing, it'll give us the same kind of output. Remove that, and you can create indices just as normal tuples. Here we'll give you an index, but let's see what it is going to do if we're not going to give it a restriction. It's going to give us, it's default into integer, and yeah, you can't use that for arrays. So if you use tuples, give them an explicit type signature. The way I solved it is there is a base type, which is a 2-dimensional index, and it is created just with a colon dot. Stole this idea from Ripa and Accelerate. They use this exact same type constructor for multidimensional indices. And it will give us a 2-dimensional index. And both of them are ints. And they now type ambiguous. You don't need to give an explicit type signature. Now, if you want to get a higher dimension, what do? You just chain it up with the operator colon greater than, and this will give you a 5-dimensional index 1, 2, 3, 4, 5. And if we ask what type of this thing is, it'll give us, it's an index and of 5th dimension. If you've never seen this, this number is in the type level, you don't need to worry too much about it, because there is also a type synonym, so you can give it ix5, it'll give you the same thing. It's every index up to index 5 has a type synonym. The problem is still with the first dimension. If we ask what type of it is, it's just a num. But we need an int. That's what we use for creating vectors. So if you have a situation where you want to create a vector and it's type ambiguous, you can give it a manual type restriction, or you can use this pattern synonym that will create an index, which is basically, it's going to be an int. It's always an int for a single dimension. And you can do the same creation of multidimensional arrays with this operator, but now it contains indices of the type from Massiv. And if you're curious, this is how it is implemented. Index 2 is very simple. It's just an operator with 2 ints. But it's a bit trickier for arbitrary dimension. If you don't need to learn this, how it works. It's really fun. I had a lot of fun trying to implement it and doing type functional dependencies, no, type family dependencies. Is that it? Anyways, this is how it's implemented. It's very efficient, and it's easy to use once you get used to it. Indices even have instances of num. So you can do something like this, and it will multiply 20 by 2 and 70. But if you wrap it with change the what do you call the priority, then it will treat them as numbers. What it's going to do, it's going to create a 3-dimensional index out of 2, multiply it pointwise by each dimension, and add a 7 to each of the dimension. So that's why you get 9, 27, and 47. It would be equivalent for me if I did something like this. 2, 2, and 7, 7. And there is quite a few functions that you can use to operate on indices. Normally, you don't really need to worry about it unless you're trying to create functions that operate on an arbitrary dimension. If you're working just with matrices, don't worry about those extra folding operators, for instance, on indices. But here's the type signature of it. Index is the type class that allows me to create indices of arbitrary dimension. And it's a regular fold L over index. Takes a folding operator, accumulator, index, and it will give you results. So we can convert an index to a list if you wanted to. And since it's a fold L, it will give us a reversed. There's helper functions that will create you that you can use to construct indices, but they're only really useful if you're doing functions, as I said, for arbitrary dimension. There is a way to iterate over indices. This is exactly what I use for iterating over arrays of multiple dimensions. So for instance, if you do a map over index, what it's going to do underneath, it's going to use an operator like that to go ahead and iterate over an array using those indices. So for example, if we do something like this is a 3-dimensional index, and here's the type signature. If you ever wanted to contribute to Massiv, writing all sorts of functions, it would be good to learn this kind of stuff. And in general, it can come in handy. But I'm not going to bore you with this, because this is not particularly important for operating on arrays. There's a way to uncons. There's a way to snark, so you can get I can deconstruct and construct indices in such a fashion. There is a way to get a particular element from an index, so we can get. Oh, this is very important. Dimensions in arrays, they go sort of outwards. Whenever you talk about a 3-dimensional array, the first index here, it talks about the highmost dimension. So it's a dimension of 5th, 4th, 3, the 3rd dimension, 2nd, and 1st. And there is no 0 dimension, because 0-dimension array is just a scalar, so there is no 0-dimension array in Massiv. Although other libraries implement it for different reasons. So in this case, we try to get dimension, the 4th dimension, and we got exactly what we wanted. But if I put it something else here, it will get that something else. This is a partial function. All partial functions in Massiv, they will have a little tick on them. I kind of abused the convention. Normally, it annotates strictness, like fold L, tick. It's in base. It's a strict fold. Everything is strict by default in Massiv, so I'm not using that for strictness. I'm using it for noting partiality, which means that if I'm gonna try to get a dimension that is not available, it will give us an exception. It's a pure exception. Try not to use it because it will give you an exception somewhere where exception is not supposed to be thrown. Something like division 0 is a pure exception that is being thrown from pure code, which is not really good, but we have it. There is a safe alternative. Any function that has a tick has a safe counterpart, and it's restricted to monothrow. So, for example, you can give it a type signature, either some exception int, and if you run it, it will give you a left with exactly the same exception. So you're not trying to catch those exceptions. It's done in a pure fashion, but you have ability to access the exception if you need it. In a similar way, we could have just done a maybe here, and it would give us a nothing. Or we can leave it off completely, and that means this thing will run in GHCI, which means it's going to be defaulted to an IO monad, and it will do exactly the same thing. It will throw an exception in IO for us. Let's leave that here. There is also a safer alternative because we know how many dimensions this index has. So we can, already has been run. We can do something like this. It'll give us 4 dimensions, and there is constructors up to 5 dimensions that allows us to do it. So, for example, here I'm trying to get a 6th dimension out of this 5-dimensional index, and in order to construct something like this, you need an extension data kinds. And if I run it, it will give me a very informative error message saying that false is not true. But that means I know a way how to make it prettier, the error message, and hopefully I'll get it to it someday. But essentially it means that you're trying to get a dimension that is not available. And the reason why I'm talking about this dimension thing, if we look at look at this type. This dim type constructor will be used in many places, so it's good to be familiar with it. But all it is essentially is just an int. There is nothing special about it. It's just a new type around an int. There is also another new type around an index, which prevents a lot of mistakes. It wasn't there in previous versions, but I thought it would be a good idea to make it even more type safe. It's a size. You wrap it with any index with this size constructor. It will give you a size data type, which is also a new type around an index. For this reason, whenever you try to construct an array, you have this size ix and an actual index. So you can just pass an index here. You'll see how often even I make this mistake, and everybody does, because we don't think of a size separately. Well, we should. The other reason why we have it here is it will prevent you from creating, let's say, negative indices. Here, instead of -3, it will create a 0. It prevents a lot of bugs this way, which is also very, very useful. And it prevents you from operating mixing index and a size. So, for example, if I did something like this, I can sum 2 indices, and it'll be very happy. But if one of them is size and another one is an index, you get a type mismatch error, which is very useful. And there are helper type synonyms. If you don't like these infix operators, it's up to you. Read up in documentation. You can create sizes with a Z, a Z4, and this is essentially the same thing. It's just pattern synonyms. Throughout this talk, I will try to use just the default notation, the default way to construct sizes and indices. But just so you know, if you see something like this, don't get confused. It's nothing special. It's just a synonym for constructing the regular way. Another thing that is available is a stride. Have you anybody who has heard of a stride before? What does it mean? No? Good. I will talk about it in a little bit more detail then. Last Zurich hack, actually, one of my friends told me about it, that it can be a very useful addition to Massiv to have a stride. What it means is if you have an array and you only want every third element, let's say, in a vector, or if it's a two-dimensional array, you want every third row and every second column, for instance, but you don't care about other elements, you can describe it with a stride. That's what it means. It just skips those rows and columns, and you only care about those that indices, the elements that under indices that are divisible by a stride, essentially. So, for example, here we have an array. It's a vector from 0 to 10, inclusive, and we give it and we try to compute it with a stride. And there is a special function that does it, compute with stride, which will, let's do this. Oh, look at that. I messed it up I was messing with it at Zurich hack. And I put a index 5 here, so that's what happened. We want to get rid of that. Okay. This essentially gave us what we were trying to do before. It gave us an array of even elements because we gave it a stride too. It gave us only elements in that are divisible by 2. But the cool thing about it is, which is what I'm going to be talking about next, cool thing about it is this thing right here, it's actually not represented by an array in memory. This is just really a function that is like an array. So whenever we compute it, we only really create 6 elements. We never create 11 elements. And this is very important and very useful. So I'm going to talk about this. I'll start talking about it right now, but we'll continue at the next session. So yeah, this is essentially a stride. It also prevents you from creating 0 because divisible by 0, it doesn't really make sense. And negative strides also don't make sense. So whenever we run this, we get a 3 and 1 and 1. And a stride of 1 is essentially an identity. You'll care about every element in the array. Let's look at.
How are you doing your validation in your constructors like that?
Good question. It's what it is a pattern synonym. So if we look at this is a pattern that takes an index and a stride, and it returns us back a stride. You cannot, there is a constructor safe stride, which is not exported by default. It's exported from an unsafe module. So if you want to shoot yourself in the foot, you can, but it's not promoted. This way, if you use a stride, it will create safely, and you can use it as a regular type constructor. So you can pattern match on it, and it just works beautifully. And there are a few instances, useful instances for it, like Q or show and such. Okay. Representation. This is, I think, it's a little too big. No, it's fine. 0, 3. Let's get this a little bigger. I'm going to start talking about this, and we'll continue. We have, I think, 8 minutes. Oh, I can talk quite a bit about it. There is a hierarchy of classes that allow us to, not allow us, that prevent us from doing stupid things. And they separate those representations and what we can do with them. The construct type class obviously means that this is the representations that we can create. Then there is load type class that allows us to load arrays, load them into memory. I'm going to talk about the process, how that happens a little bit later. There is also source arrays. These are the things that we can compute, that we can operate on. We can map things over them. Manifest arrays is kind of like source arrays, but they are represented by the actual memory. So the arrays I was telling you about before, primitive, unboxed, boxed arrays, they are all manifest arrays. So they allow you the order one, constant time lookup in memory. That's why they're efficient. Source arrays, you cannot do that. If you call evaluate, if you try to index it with a special function, then it will evaluate an element at this particular index, but it will do so on every call to this index. There is an example a little bit below. And there is also mutable representation, mutable type class, which also all of the representations I talked about, they're also mutable, so we can do mutation on it, and I will have plenty of examples of how that's done. But as you notice, every mutable array is also a manifest array, so, but not that, vice versa. There is every manifest array is a source array. Therefore, all of these representations that I'll talk about, they can be used as a source. They can also be loaded into memory. So what does it mean, loading an array that is already in memory? It's essentially a copy. And let me go ahead and go over some examples. Okay, here we construct a sort of paraboloid. Now we're already familiar with the multiple dimensions. So we create here an array of n by n, and we give it a function that takes an I and j, and applies a function that is just a square of them. It's not terribly important what it's do, what's the values behind it. But what is important is this d here. It's a new representation, and there is a bad news for you. There is some more of those representations, and they're unique in what they can do. And it's good to get yourself familiar with all of the representations, because it allows you to write efficient code. And these type classes above usually, most of the time, prevent you from writing the inefficient code. I will talk about some pitfalls that unfortunately cannot be solved, but they're pretty rare. So we create here an array, a matrix with the elements that are double. Here it is. We create this array. Let's look at it. And there it is. This is a two-dimensional matrix. Yeah, cool. And we can try to run some operations on it, like we map a function, which is we'll add 10 to each element, and then we want to sum it. And it gives us a result 350. I don't know why it's here. Let's run it again. There you go, it's 350. Now, I was telling you about manifest representations. That's what I call them, manifest representations, the boxed, the unboxed, the primitive. If we would have used those representations, and not in Massiv, but in some other library, for instance, the array library that is in base. If you would map something, map a function over an array, it would create an array again in memory, another array. Memory allocation is kind of expensive, and then you need to do garbage collection. So this is we always try to avoid that, especially if we're not going to use that array more than once. And especially if we want to then fold over it. So if we sum all those elements, this array really never needed to be created in memory whatsoever. So this is exactly what happens here. A delayed array is just a function. In this operation here, this array never came to existence. And this process is called fusion. We fuse those operations together. GHC tries to do that for you automatically for lists, which is very easily broken. As Neil Mitchell told me a couple of days ago, yeah, if you even blow on this list, it'll break the fusion. And he's absolutely right. It's very easy to do so. With the approach here, with this D representation and a couple others, you control the fusion manually. It's up to you when you fuse those arrays. So, for example, I could have run compute as P, and it would still give me the same answer, but here it would actually allocate an array in memory. And we'll talk about this computation process and how it works. But for now, I just wanted to give you an idea, a sense of how this works. And in 2 minutes that we have, I want to prove it to you that it doesn't come into existence. This is just a ridiculous square, I call it, because what we're going to do, we're going to call this ridiculous square with the argument max bound. Technically, this would blow up the memory, right? But if we run this, what it's going to do is going to give me an element of this array. Oh, here's the. I'm gonna explain this in a moment why it works. But if I'm gonna evaluate an element in this array, I can do that. This is exactly what's in there. And then I can use a stride. As I was explaining to you, it will get basically it will give us 3 elements that are divisible by this big number. And we can go ahead and get this stride. This is how the stride looks like. And this is the array that we get. But what's up with this? When we compute it, it actually computed for us. And it created an array in memory, and we were able to index it. Well, what's the size of the... I'm going to finish up, but what's the size of this? The size of the array is max bound by max bound, which is just 1. So whenever I tried to compute it, it was actually creating an array of 1. So don't deal with arrays that we have these huge sizes, because that's dangerous. Okay, we'll continue later on. Now it's break.